So I'm Hao Chen Dai, and some of you might know I'm one of your TAs, and hopefully so today what I'm going to help you is doing the shortest path is a very famous problem in the algorithms, and hopefully I can help you to understand these topics. So I think most of you have the experience using the Google Maps to find the shortest path from where you stand to some point like the destination you want to head to, right? So nowadays the Google Maps are smart enough to give you few options like shortest path in length, or shortest path in the time cost, or shortest path in the fuel cost, right? So the first thing that we want to talk about is how do we solve this problem with our knowledge that we have already been studied. So we can think of the graph. We can use the graph to represent a map, right? And so there's few notions that the reality concept can correspond to. For example, there's a intersection of the street. Then you can use the vertices to represent the intersections. And also you can use the edges to represent the street, one-way street. And also you can use the weight on the street to present how long this street is, right? So what we are going to talk about is obviously a graph problem. And the first thing, okay, we want to formulate this problem like below, like here, given a weighted directed graph. Right, so vertices, this is the edges, and this is the weight that on the edges. We want to find a direct path. P such that starting at a source and ending at T. So this is your destinations. And it can minimize a function below. So this function is called the sum of the weight, which is equals to so this is the weight on the edge connecting U and V, vertices U and V, and these edges must belong to the path that we trying to connect the source and the destinations, right? We want to minimize this function. So there's another function that we introduced to help you make the problem seem more clear. There's a delta function. So the delta has two arguments. So this is the source, this is the destination, equals to the minimum over P of the weight function, sum of weight functions that we mentioned before, if there is. If there exists a path. For those we can't find a path between them, it will equals to infinity. So today we are going to talk about very specific shortest path problem. It's called the single source shortest path. Let me write this down. Or we can abbreviate it as the SSSP. I would just abbreviate the shortest path as SP to save time. So you might think of, okay, so there's a single source shortest path, and also there is a shortest path problem called all pairs shortest path that we will mention, not in this class, maybe in the later class, I don't know. So what we are going to talk about today is only the single source shortest path. Basically, for this problem, as you can tell from the name of it, okay, let me write on another board. Okay. So it's given a graph similar to the previous one, but with a source. You're going to choose a source from that graph, and we are calculating all the distance starting from the source to every other vertices in this graph. Find the delta from the S to the V for any vertices belongs to V, but except for the source S. So this is the formulation of our, yeah. What's
so delta is the path, correct?
Yeah. Or it can represent, it's actually telling you, it's a number, not telling you the length of the shortest path. You can understand that way. Yeah, actually we were just treat it as a function that returns you a scalar. Yeah. So we are basically finding a shortest path, the union of the shortest paths from the source to the every other vertices. And you know, these passes can actually form you a shortest path tree, right? It's like, so what what makes you think of when we talk about the shortest path tree? Yeah. Yeah, Dijkstra we'll mention later, but what about the thing that we have learned before, previously? Yes, exactly. It's like the minimum spanning tree, right? It's always about finding the sample weight, the minimum sample weight, and also you're trying to connect all the vertices together, right? But do you see any difference between the two problems? Yeah?
They all start from one place.
Yeah, one place.
I was going to ask, so this is basically finding the shortest path to all vertices, except for the starting.
Yeah, starting from the source to all the other vertices in the graph. Any other thoughts? So think of the graph we are studying here. It's, yeah. Yeah, it's directed, and the MST is not directed, right? And this is the rooted one. The MST is not rooted, right? So here's another example. So some of you might think of, okay, how about we trying to solve the shortest path problem with some idea from the minimum spanning tree, right? And here is an example that I would like to show you that the minimum spanning tree is not necessarily a shortest path tree. So on the left-hand side, the red one is the minimum spanning tree. And on the right-hand side, the blue one is the so-called the shortest path tree. You can see the edge have the weight 8 and the edge have the weight on 4, it's different, right? So for the spanning tree, you got 2, 3, 4, 5, 16 together, but for the shortest path tree, you got the 3, 5, 8, 12, 14, 16. And you can see here is actually a non-directed graph, but actually for the graph on the right-hand side, it's basically a directed graph, but on both directions, they have the same weight. So just so you know, if you have any question, yeah. So another thing that we want to mention before we dive into the algorithms that we study today is that we are not talking about any graph with a negative edges, negative weight. At least at the first algorithm we talk about, we are not talking about any negative weight. Do you see a reason why? Yeah.
Because you can loop through and keep finding a shorter path.
Yes. So that's about how you define the shortest path, whether you can find the shortest path in a graph, right? So just imagine if you are having infinite choices of the path, can you find the shortest one from them? Here is the example that I would like to show you. So here is a graph that with the negative edge, but also it got the negative cycle inside. And you can see the sum of the cycle will be 2 minus 8 plus 1 plus 4, which equals to minus 1, right? So whenever you travel through this negative cycle, you will have the shortest path, length of shortest path go down by 1. And you can do that infinitely, and you will never reach a minimum of that, right? So this is why, this is the reason we will not talk about the, yeah?
So is this only when there's a cycle? What if there's no cycle?
If there's no cycle, the negative edge is fine, yeah. You will just travel through, if you can, so the thing here is, if there's a finite choices of paths between the S and T, right? You can definitely find the minimum from the finite choices, right? So if there's no such finite choices, then you can never find something like the shortest length between them. So in, yeah.
Yeah, so in this case, if we look more and more time, the weight will become smaller.
Yeah.
It's because the weight is negative 8, but if the value is negative 1, I think there are the smallest, shortest path.
So basically, the key here is you can see the sum of the negative cycle is minus, right? It's the negative value. So you can do that infinitely to make your length of shortest path go, not the shortest path, but the length of the path going any further down, right?
Yeah, but I mean, if the volume negative 1 is not very big, like it's negative 1, so...
You mean the 8 going to negative 1?
Yeah.
Yeah. That might give you a shortest path, but yeah, so that's the reason we want to talk about, that's actually it's not the negative cycle, right?
Because the sum is not negative.
You can understand that way, yeah.
Okay.
Yeah. So the key is not having or not the negative edges, but if you were find the cycle, sum of the cycle will go into negative. If the cycle will go into negative, then you can have the sum of weights keep going down. So after talk about the negative cycle, we are going to talk about the very generic algorithm of all the shortest path algorithm we are talking about later, just like the minimum spanning tree. So it's called the only okay, let me abbreviate it. I will just abbreviate the shortest path as SP. Or it's called the forward so this stands for the single source shortest path. So also here are a few notions that I like to introduce to make the solution of the problem more clear. So for each we'll assign 2 attributes to every vertex. The first one is called the dist of V. So the dist of V is the length of the tentative. What do I mean by the tentative? Yeah?
We're not sure if it's as shortest path, but we're just going to say it might be.
Yeah, it might be. At this point, it is the shortest path we can find, right? And another one is the it's the predecessor or we say it's the direct predecessor of V in the tentative shortest path. So we'll only give every vertices 2 attributes, and then we can actually find the shortest path to this vertex by using the predecessor. And do you see why only the predecessor of the V will work to find the shortest path? So just imagine the predecessor is like the parents of the vertex, right? So if you know the parents of the parents of yourself, and your parents know the parents of themselves, then you can find the shortest path, like starting from yourself all the way to the source, right? Yeah.
What does that bottom part say? Just below.
Tentative shortest path. So that's the reason only recording the predecessor of the V is enough to record the shortest path from the source to the vertex itself. And also here is the, yeah.
Does this mean we build the shortest path from the end to the beginning?
No, we are starting our shortest path from the source to the vertex itself. But we know the predecessor of itself, right? We can go back to, and then we can construct a path, and then we're starting from the source to all the way to the vertex. Yeah. Okay. So after introducing these 2 concepts, I'd like to the first thing we want to initialize the 2 attributes, right? So the first step would be the So we will assign the dist of the source as 0, right? So because we know it's the starting point. And also the predecessor of the source is also be now. Because we know there's no such predecessor of the source regarding the finding the shortest path to all the other vertex. For all vertex that's not equals to the source, we will have the assignment So at the beginning of the algorithm, we will assign the distance of every vertex as the infinity because we haven't found any shortest path yet. And also the predecessor will also be initialized with now. Okay, so this is the first step of the framework. Another thing that we will constantly mention in the following class is called the tense. So what does tense means? So if there is a vertex called U plus the weight of the edge that connect the U and the V is less than the dist of V. Then we call the edge connecting U and V as tense. So that means we are finding some alternative paths that can give the V an even shorter path. All clear? And another thing is, what if we find the tense path we are going to do next is called the relax. So basically, if we find something, the relax. There's no if in relax. It will update the dist of V with the dist of U plus the weight of UV. And also updating the predecessors of V with U. So if we find any path that the U is the predecessor of V, then we will update the dist and the pred with the corresponding values. So, okay, after we have introduced the initialization, the concept of tense, the concept of relax, so we are going to the algorithm of the generic for shortest path algorithm. Let me see. So the fourth will be quite simple. The first step will be initialization. The next step will be a while loop. While there is at least one tense edge. Then we will relax all the tense edge. So we'll keep doing the relaxation until that we cannot find any vertex can update the distance of the distance of V. We cannot find any U that can update the distance of V to make the path even shorter than the current one. Yeah.
Would we also have to relax V if U becomes relaxed and the value of the distance of U changes?
Yeah, so this is the while loop, right? If there's such path that we can find, then we'll relax it until we'll keep this doing again and again and again, then until we cannot even find any path that is tense, any edge is tense, yeah?
Wouldn't this result in an infinite while loop with an example like the one where it has the 2 minus 8, like the active loop that's negative? Wouldn't that be an infinite while?
Yeah, so this is reason why I mentioned that today we are not talking about, this algorithm will not solve that kind of problem, right? So that's our prerequisite. Okay, so except for introducing this very generic algorithm, there's also a very important property of the shortest path, which is called the optimal substructure. Let me see which one that I can get rid of. Okay, let's see this one. So this is the optimal substructure. And so these property argue that any subpath of the shortest path is also a shortest path. Do you see the reasons why this would hold? So just assuming that, okay, so let me say this. If there's a path, okay, it consists of V1, V2, all the way to Vk, right? This is our, being said, the shortest path, right? And we argue that if there is a subpath, it's called the Pij, which is a portion of the previous path, right? It's all the way from Vi to Vj, that this is not a shortest path. We argue that the Pij is not the shortest path. Then we can find some shortest path called the P prime ij that is less than the Pij, right? And then we can basically replace the Vi to Vj part with the new P prime ij. And then we can construct an even smaller shortest path, right? And this is contradictory to our initial assumption that this path is the shortest path, right? So this is how the optimal structure is proven. So always keep this very, yeah.
So is that kind of saying like if there is a shorter path, we would have taken it, kind of thing?
Yeah. Yeah, so that's no longer a shortest path, right? If we can find another subpath is even shorter than this subpath. Yeah. So basically, it's saying if there is a shortest path and all the vertex on that shortest path is basically having its shortest path to the source. So that is the thing that you have to keep in mind for a long time, at least for this class. Okay, so after we have the framework of the very abstract and generic Ford SSP, we are finally going to the very famous algorithm called the Dijkstra, just as the gentleman just mentioned about, right? So actually, the Dijkstra algorithm has been invented by a lot of people. And the reason why it's called Dijkstra is because Dijkstra is the first one to invent that. So typically, we will call this kind of algorithm as Dijkstra. And so let's first take a look at how the pipeline of Dijkstra looks like. And we will add we'll put a constraint on this Dijkstra. It's called the non-negative Dijkstra. And the pseudocode of this Dijkstra will look like, first step is also initialization, right? And after initialization, we will have a structure called the priority queue. I will write here. Just like we did in the minimum spanning tree, right? There is a priority queue in the Jarnik, I think. So for all vertices, we will insert the vertices with its initialized dist to the priority queue. So the key of this priority queue will be the distance of the V. And then we come to, just like the Ford SSP, right? It goes to a iteration while Q is not empty. Oh, sorry. It's not empty. What we do is extract the minimum in the priority queue to the V. So this is the function that priority queue would have, and seems like I make the font too large. If UV, the edge of UV is tense, if the UV is tense, what are we going to do? We are going to relax the UV, right? No. There's a for loop before this one. We have extract the U for every outcoming edges. We will traverse for these edges. For all these edges, we are going to a if condition to see if the U to V is tense or not. Okay, I will leave this here. Going to wipe this one. So it will continue here of the Dijkstra. So it will basically be if U to V is tenths, then we're going to relax U to V. And also we're going to push or update, it's called the decrease key, with the new distance to the priority queue. So this is basically how the Dijkstra works. So to give you a very intuitive concept of how Dijkstra is going, I will do an example, help you do example to get you a more clear image of Dijkstra. So here's the graph that we are going to perform the Dijkstra. And you can see the priority queue only got one number, right? Because I have omit all the infinity coming after the non-infinity numbers. So we are going to, so the A will be the source. We are going to starting at the source. And you know, the source, the distance of source at this point is 0, right? And the priority queue will be coming first with 0. And then we know that there is a two outcoming edges of the vertex A, right? So we are going to traverse the outcoming edges of the U. So the U here currently is the A. So the first one will be the edge of 4. The second one will be 3. And we know 3 plus 0, right? This is the relaxation. 3 plus 0 equals to 3, which is less than the infinity. And then we're going to update the B from infinity to 3. And also we will do the same thing to these edges. 0 plus 4 equals to 4. And we are going to update the infinity with 4 right here. And this is the first iteration in the while loop. And then whenever we are updating the tenth edges or these we are doing the relaxation, we have to decrease key, right? Here is the decrease key. Once we do the relaxation, we are going to decrease key, which is updating the distance in the V. So once the value in the priority queue is updated from infinity to some numbers, so then the first two items in the priority queue will be, the first one is B, because B got length of 3, and G got the length of 4, so the B will come in before the G. And the next step is the B are being extracted from the priority queue, right? We are going to look at the B. So B got two outcoming edges. The first one is 7. The second one is 12. And we know that 3 plus 7 equals to 10, which is larger than the current distance of G, right? So we are not going to update. and we know 3 plus 12 is 15 is less than the infinity, then we're going to update the C. So after we relax the C, we are going to push the C into the priority queue with the 15. And now the G is at the top of the priority queue. Next one we are going to traverse is the G. So G got 2 edges, outcoming edges. One is 0, one is 5. And it will be updated by 4. This will be updated by 9 because 15 is larger than 9, right? And so on and so forth. We are going to push this C and E into our priority queue. And we'll do the same thing to the E. So these are infinity, so it will be updated by these numbers. Okay, and you can see at this point, actually this is already the shortest path tree for this graph. And whenever you are going to the D and F, you can see there's no outcoming, the F have the 2 outcoming edges, which is the 8 and 4, but actually it cannot relax the 2 edges, so it will just stop here. So this is how the Dijkstra works. So the key in the Dijkstra here is the priority queue. Why are we going to use the priority queue? So it's basically making sure the vertices that coming before the vertex, so let me say it this way. If we are going to extract one vertex, right? This is the vertex that we extract first. And we want to make sure that the vertex here is already had the shortest path. And based on this shortest path, we want to update the vertex coming after this vertex in the priority queue. Yes?
Will you need to implement a tiebreaker? Or would we assume that,
Well, the tiebreaker doesn't matter. Because if we are trying to find the shortest path, right, we are only caring about the length of that. So whether there's more vertex in the shortest path or not, we are not caring about at this point. So here, for this priority queue, there's very interesting property of the Dijkstra. Okay, I will just wipe this one. So there's a Do you guys want to take a break? Yeah, take a break for 5 minutes. So, I think some of you might thinking about how can we guarantee the vertices that pop out from the priority queue is already the shortest path, right? How can we guarantee that? If we can guarantee that, then we can say, okay, this mechanism works, right? Okay, so we are going to try to prove that this is going to work. The first 2 lemma that I would like to prove that is very critical to give you the final proof of the correctness of the Dijkstra. The first lemma is argued that for the graph, we are always talking about the non-negative edges in the Dijkstra. So I would just omit that. So for all I less than j, I will explain this later. We have di less than dj. You might wonder what is I, what is j, what is di and dj, right? So we assuming that in this while loop, every time we extract a vertex from the priority queue, we call at the ith iteration, if it's ith iteration, it will be the ui. We'll call this as ui. And the distance of ui will be abbreviated as di. So this is what I mean by I and di. So this argument can be rephrased for the vertex coming after the ui. So uj is coming after the ui in the priority queue, right? Then we will definitely have the distance of ui larger than the distance of distance of uj larger than the distance of ui. So the distance in the priority queue is always going up, monotonically increasing. Yeah.
I was going to ask, should that be less than or equal to? Because the path lengths can be zero.
Yeah. Of course, there can be zero, but I think this is not very how to say. This is not very typical example here. So we were already talking about the weight of the edge is going to be positive. We are not considering about the zero one. Yeah. So this is the first argument, and we are going to prove why is that. So quite simple. So there's only two cases, right? Okay, I will just there's two cases. So you can see here, inside of this loop, right, you got if the UV is tense, then we'll relax the UV, right? And what if UV is not tense, then we're going to do nothing, right? So there's two cases. The first one is so the first case is UV is tense. So then we are going to, inside of the if operation, right? We are going to relax the U and V. So which means, okay, not UV is tense. UJ is tense. And then we will have the DJ. Oh, or we say in this situation we'll do to be more clear, it will be UI plus 1, right? Because we know that the one that coming after UI will be the UI plus 1. So the DI plus 1 would equals to DI plus the weight of UI plus 1, right? And this is going to be larger than the DI, because we know this is going to be positive, right? So the case 2 is we are not going into the if condition, so the U to V is not tense, so which means that DI plus 1 is not going to be changed. So the D plus 1 is not changed. Do you see a reason why the DI plus 1 will be larger than the DI? Any thoughts? Considering the priority queue, what's the property of that? Yeah?
Well, if it was, oh wait, I was going to say because if it wasn't tense, then it would have to.
So if it wasn't tense, then we're going to do nothing. So this DI plus 1 is not going to be changed, right? It will stay the same. So why we can also argue that the di plus 1 will be larger than the di. So the priority queue are actually guarantees that uij is coming after the ui, right? The reason why ui is popped before the uij is because the di is less than the di I plus 1. So that's the reason why this is also going to be larger. di plus 1 is going to be larger than the di's because of the priority queue. Because the priority guarantees that the di is popped before the di plus 1. Okay, so then we prove that for all the I less than j, then we will have the di less than the dj. This is first lemma we are going to talk about. Then comes to the next one. Lemma 2. So the next lemma is going to argue that the vertex V will be extracted from the queue at most once. Which means whenever we are going to extract one vertex from the priority queue, it's never going back to the priority queue. So this is what the lemma 2 are talking about. So to prove this, we have to use the lemma 1, which is it's monotonically increasing. So basically, we assume that at the ith iteration, we will have the ui extracted. This is the ith iteration. And at the jth iteration, we are going to reinsert the ui into the priority queue by the decrease key. And at the case iteration, we are going to re-extract this vertex. So we have I less than j less than k. So it happens first, second, and happens last. So we have So we have 3 di, dj, dk. So can you see any relationship between the di and dj here? So it's equal or less than or larger? Which one? Yeah? Yes. Why is that?
Because of the priority queue.
Because it's extracted, right? We are going to insert it. So, which means we are going to the decrease key, right? Is that correct?
Yeah.
So that means the u to v is 10, means there's an even shorter path to update the dj, right? So that means the di will definitely larger than the dj. And can you see any relationship between the ith iteration and the kth iteration?
K is going to be constant K.
Yeah. Why is that?
Because the same thing, we decrease the D.
So we re-extracted, right? So the dk should be larger than the, sorry, it's not this one. The dj and dk is actually the same thing, right? We push that into the priority queue, and then we re-extract it, so the di is actually basically the dk, right? I'm asking about the dk and the di. What's the relation between these two? Using the lemma 1. Yeah.
Di should be less than dk.
Yeah. So di will be less than dk, right? So we know that the dk is the same thing as dj, right? So we just use another notions that d prime is less than di, and d prime is larger than di. So this is a contradiction, right? So which means this argument is correct. So the vertex will also be extracted from the queue at most once. Okay, after we have the two lemmas, I think it comes to proof that the Dijkstra's correctness. Okay, I will make the lemma 1 here. Okay, our previous argument is that possible that the vertex, yeah.
So just to be clear, so for lemma 2, we can reinsert V, but we can't re-extract V. Is that right? Like into the priority queue?
So if the V is extracted from the priority queue, that will be inserted again.
It will never be inserted?
Yeah.
Okay.
So previously we were going to say that whether it's possible that for any vertex, say the U, coming after the V, so this is the priority queue, that V is coming before the U. Is that possible that after we extract the V, the U can actually give the V an even shorter path? Is that possible? So if that is not possible, then the Dijkstra can be proven that it's going to be correct, right? So here are a few assumptions we'll make. The first assumption is that assume that there's a vertex that have a property that distance of x is larger than the delta s to x. So this is our argument. That means that the answer given by the Dijkstra is not correct. We can even find an even shorter path for this x, and assume that x is the first vertex that has this property in the priority queue. First thing is x is the first one in queue such that have this. The second assumption would be assuming P is the real shortest path from S to X. So the third one will be let Z, there's another vertex called Z that is coming after the X in the priority queue, but it will also be in the shortest path, real shortest path. So these are first three assumptions. And the next thing is we assume that there is a vertex called Y that is the predecessor of the vertex Z. So these are four concepts or notions that we want to present to help us to prove. So we know that the Z is the predecessor, the Y is the predecessor of Z in the shortest path, right? So the first thing that we can have is the delta Y Sy will equals to distance of Y. So this is the distance given by Dijkstra, and this is the true shortest length of shortest path. And because the X is the first one that doesn't hold this property, so this will hold, right? The Y would hold. And the second one is the distance of X will larger than the distance of Z. Why is that? Yeah?
Because Z is still in the priority queue?
Yeah, because of the lemma 1 I just wrote, right? It's monotonically increasing. The third one is the delta S to X equals to delta S to Z, Z to X. So for this, what's the argument here? Why we can say this is correct? Thinking about the optimal substructure, right? if this is the shortest path, and the z is in the shortest path, then we can argue that the shortest path length from S to Z plus the length of shortest path from Z to X will equals to the shortest path length of from X to X, right? Yeah.
Can you elaborate more on number 3 over there? I got a little confused there.
So we have just talked about like whether it's possible for the vertex coming after some vertex can give the extracted one even shorter one, even shorter shortest path, right? This is the one that coming after the X. Yeah. So this is third one. This is correct because of the optimal structure. And the last one, okay, here is going to be the proof. Not going to this one. Seems I have to wipe this lemma. Hope you have keep that in mind. So we already have the dist X is less than dist Z because of the monotonic property of the priority queue. And this is equals to the delta S to Y and plus the delta Y to Z. This is because the Y, oh, I think I've wiped that out because we assume Y is the predecessor of the Z in the path, shortest path, right? And then we have delta S to V, S to Y plus delta Y, not this one. So this is the weight connecting the Y and Z plus delta from Z to X. What would this equals to? Just simplify these three terms into one term. Any ideas? Using delta equals to delta what? Yeah.
Delta S to X.
Yeah. Right. And it means that this is delta S to X is larger than the distance of X. Right? But we assume at the beginning, we assume that the distance of X is larger than the delta S to X. So this is another contradiction here. So we have proved that it's impossible for the vertex coming after can update the previous one already being extracted from the priority queue. So we can make sure that whenever the vertex pop out from the priority queue, it will be the finite. It will be the final answer in the shortest path. Any questions here? Yeah.
So essentially, once a vertex has been updated from infinity, that's the last one that's going to be updated.
No, it doesn't mean that. Because what I say is once it's extracted from the priority queue, because it's at the top of the priority queue, then it's the final answer.
Okay.
Not, yeah, it's not,
taken out of
yeah, kick out of the priority queue. So I think we have proved this. The last thing I would like to talk about is very simple, which is the complexity of the Dijkstra. Won't take too much time. So we know that for this insert operation, how many times at most it will reach this? Yeah, V, right? So for this, the insertion will be V times log V, right? Because we know the insert of this priority queue will be the log V complexity. And what's this line, how many times at most will be executed? Priority queue, about the priority queue. Yeah, also V, right? This one will be V log V, because we know the extract mean will also cause log V complexity. And about the decrease key, for this, how many times at most? It will be E, right? So we'll traverse every single outcoming edges of one vertex. So it will be E times. So this is also will be the decrease key is the log V complexity, right? So for this, it's always going to be constant time complexity. If this is the E times some constant one, like right here, and we know the complexity will probably approximately be V log V times 2V log V times the E log V, right? And we know that, so which term is the dominant term, you think? E times log V or the V times log V? Yeah.
Depends on how many vertices or addition you have.
Yeah, but you know, like the E will be at least V minus 1, right? And at most, V times V minus 1, or is something like the V square. So the E times log V will be the dominant one. So basically, we can say the complexity of the Dijkstra will be E log V. Yeah. Yeah. Also.
This is also because it's directed, right? Not because it's not undirected. If it was undirected, it would be a little bit different.
Yeah. Well, for the undirected, the only thing is this term will be different, right? So it will be from V all the way, summing from V all the way to the 1, right? So it will also be something like the V square. So it still holds. Yeah, so that's pretty much of today's lecture.
Thank you.
Thank you.